Ist heute schon wieder der 27. Oh Mann. Jo. Ist ja bald schon wieder Silvester.
Bitte?
Ja. Ich weiß auch nicht, warum haben wir denn nur noch einen Bildschirm?
Okay. Hello, 9 o'clock here in Germany after midnight. A very warm welcome from my side to our CO2 webinar here in Frickenhausen at the company BOCK. My name is Michael, and together we do the webinar. Today we do the webinar together with Danfoss, with the colleague Knut Schlicht from Berlin. Before we start with the webinar, for all of you who are new with this webinar part, I just show you a short the webinar manual. You can work with that. I mean, during the presentations, if you have any questions, I think it's the best if you just
Raise your
ask
hand.
the question
Raise.
right in the presentation.
Yeah. You have
Yes.
two options. One option is raise your hand if you have an
Yes.
urgent question.
That you can do here.
Otherwise, you can type in your questions in the field. Yes.
That's also possible, yeah. Normally, you are muted when you want to talk. You please unmute yourself here. You can select the screens afterwards if you want to see the presentation or if you want to see the screen with us. You can select your computer audio, change the language if necessary. Yeah, you can change the language of this site, but not, of course, our language. We will do that in English, this webinar, of course, because we have participants all over the world, from all over the world today. And yes, that's the start. What are we going to do today? We will do in the morning, here in Germany, this morning, like I said, 9 a.m. From 9 a.m. till approximately 11 a.m. We will start with CO2 systems. We will start with Knut, with the parts of controllers. And he will show you the whole CO2 system, how it works and so on in the theory. When he is finished, I will start approximately about 10 o'clock, something like that. Then with, I will show you our compressors. And then we will have a break. And 1 p.m. We will start the second part where we will do the commissioning here on our wonderful CO2 rack system. This will be, of course, the practical part, and we hope that we can show you a lot of things here right on the rack, how to handle CO2, how to start, and all these things.
How to fill.
Yeah, today we will even fill, not complete, but
No, for sure not.
I think 10 kilograms are missing today, and that's what we're going to do in the afternoon. And then, yes, maybe if you have questions, then at the end, we will have a small discussion at the end of the webinar, approximately about 3 p.m. Hello? I think we have problems with the sound.
1, 2, 1, 2.
Both? Just a break, we have a problem.
Are we online?
Okay.
Now we are back again.
Now we are back again. We had a small problem, but okay, everything is running stable now. Good. So that's what we are going to do today. And now I think, yes, like I said, I give over to
Yeah,
Knut.
please.
He will start then with his part, and I will see you later, guys. Have fun. Bye-bye.
Das machst du aber nicht jetzt. Das machst du nicht jetzt. So, my part. Also, a very warm welcome from my side. My name is Knut Schlicht. I'm 55 now. I'm a real Berliner. I live in Berlin, born in Berlin. My roots are in Berlin, so I have a lot to travel to come here. I'm responsible for technical support, all of controllers and all the electrical things. Okay, so, but now my presentation is gone. I see the... Ich weiß auch nicht, warum ihr das jetzt machen müsst. Nee. So, here we are back again. Ich bitte dich, lass es doch einfach, Frank. Seid ihr jetzt fertig mit dem Umbau? Okay. So, back to the presentation. What I want to show is this is a small overview what I want to present. If you have any questions, just please type in. I will see it on the second screen now. I'm so happy that the second screen is there. And if you want to discuss direct, then please raise your hand, and our colleague Yanni will make you that we hear your sound. So, first of all, some facts about CO2. I think everyone will know this, but here it's a small summary. You know, high volumetric cooling capacity, so we can even get smaller compressors and smaller lines. You know what we discussed, why we did not have the general refrigerant is that the ODP and the GVP is much lower than the other ones. But you have to recognize that we have 2 points of CO2 that is very important. One point is the transcritical point at 31 degrees, 73, let's make a round number, 74 bar. And the other point is the triple point. So you have 2 points, one on the high pressure side and one on the low pressure side. The high pressure side is not so important because we are controlling right through this point, and we are controlling our systems also above this point. So you just to remember where is the CO2 system is controlling subcritical or transcritical. You have to remember when we are talking about transcritical, it's important for the heat recovery. Here in our region for the heat recovery, in other regions where you have very high outside temperatures, there we always control our systems with in a transcritical situation. On the lower side, there you see CO2 has a triple point at minus 56, make a round number, minus 57, it's about 5 bars. So it's not possible to get any rooms colder than, I would think, minus 48 or 45, something like this, because if you want to have such low temperatures in a cold room, for example, then you have to expand normally lower than this point. But at minus 57, it is the end, because down below you have ice. You always have to remember at lower than 5 bars, you have CO2 ice. So it's also important for starting a new system. If you evacuate the system rack like this one, and you want to fill it now, you do not fill with liquid CO2. First of all, fill your systems with gas. Go higher than 5.18 bar. Make it clear. Go higher than 10 bar, then you are very safe. And then you are able to fill liquid in your system. Okay? So here the history, where we are coming from and where we want to go. At 2007, we are working now for approximately 15 years with CO2. There it comes booster systems. Then the next steps was the parallel compressors at 2011. Then the next step was gas ejector and liquid ejector. I will explain how they are working and what is an injector. And in the future, we from Danfoss think that's only cost reduction and the systems has to become more simple. So here are the three systems in an overview. A normal booster system, starting at the empty compressors, compressing on the high pressure side into the gas cooler. Gas cooler, at the end we have an expansion valve, high pressure expansion valve, where we expand from the high pressure side into the receiver. In the receiver, we dividing liquid and gas. First of all, liquid going to the empty cooling cabinets or cold rooms. Further, liquid going to the LT. From the LT suction side, going into LT compressors. LT compressors boost their high pressure side into the suction side of the empty compressors. And a special part here, we have a gas bypass valve. So this valve is controlling the pressure in the receiver. So we have several circuits. The controller of the empty compressors are controlling the suction side, the pressure of the suction side. This controller for this high pressure valve is controlling the pressure of the gas cooler side. And this valve is controlling the pressure of the receiver side. Okay, so the next step was parallel compressor, how it's working. So you see here also on the high pressure side our empty compressors, but parallel, that's why we call it parallel compression, there is another compressor. Why we build it in? Because when we are working in transcritical situation, the empty compressors are working well. They can control and they work with high pressure side, but they are not working with a perfect COP. If the high pressure side is going to a transcritical situation, then you have to remember that you have a very big differential between high pressure and suction side. So the COP of these compressors are going bad in transcritical situations. So what can we change? The only thing that we can change is to reduce the mass flow in this line. How do we reduce this? When we start a parallel compressor, this valve will close. So on the transcritical, in a transcritical situation, there you divide a lot of liquid and gas into in the receiver. And when we want to reduce this mass flow, we stop working this valve and controlling the pressure in the receiver over the controller from the parallel compressor. The other circuit we would not change. Okay? So if we have here an opening degrees of this valve, that we have a mass flow over this valve, a mass flow that we can start this compressor, then we will start this compressor. Okay? The last development of our system, of a CO2 system, was to build in an ejector. An ejector is nothing new. You have to remember that at the starting with the steam trains, the steam trains, when they stop in the station, you have to also cool some parts of the trains. So there would a development ejectors. Also in old steam trains, they build in ejector. They have a lot of power, a lot of steam. They put it into a small nozzle and control it, divide it into smaller pressure. And there they find, okay, if we put there a line in, then we have a suction over this line. But I will explain how an ejector will work. We come back later. So far, these 3 generations of our CO2 system. First of all, booster system. The first development, parallel compressor. Why is it clever to build it in? Because we are working here in a perfect way. We have a constant suction side. And so this compressor is working with a good COP. So we have a wonderful COP here above on the empty compressors. Next step was parallel compressors and ejectors. Some pressures in our system. Normally we have on the high pressure side, we are working between 50 and 110 bars. On the liquid line, it's a part of the design of how do you want to design your system. But normally we are working in the supermarket, we are working between 32 and 37 bars on the liquid line. On the suction line of the LT compressors, we are working between 13 and 16 bars. And on the suction side of the empty compressors, we are working at 25 up to 33 bars. Here we make a point. 28 bars is minus 8.1, and 90 bars we are working at 35 degrees. Okay, so far. And here you see the mass flow when we are working in transcritical situation at 90 bars. We are sorry. Ja, as always. Das ist aber nicht so die. Aber hier, das ist nicht so die. Da kriegt man Krampf. Ja, geht schon. Okay, here we are back again. Sorry for interruption, aber sometimes the sound is gone. We don't know why. Mass flow 100% coming from all over the parts has to go over the empty compressors, 100% going to the gas cooler, 100% going to the high pressure valve. But here, when we are working transcritical, we are dividing it in 57% liquid and 43% gas. I will show later why it is so. It's always so. Then we are coming back with 57% on the suction side of the empty compressors plus 33 from the gas bypass, and then we are going 100% back into the gas cooler. Here we show, or I will show, a booster system with parallel compressor, with normal gas bypass and empty compressors and LT compressors in an enthalpy pressure diagram. Here you see the several parts start at the LT compressors. LT compressors down below here from 1 to 2. We have the compression of the LT compressors. 3 to 4. We have the empty compressors. 4 to 5, gas cooler, high pressure valve, gas bypass or receiver pressure control, and the empty and LT expansion. The working pressure. Working pressure is another thing that than design pressure. Working pressure, we are working on a high pressure side, 45 or 50 bar up to 110 bars. Normally you can drive your system here at 110 bars, but I will show later it's not clever to do it as high. In the liquid line, between 30 up to 45 bars. Suction side, we get from the compressor build manufacturers, we get this design pressures, okay? But the design pressure on the high pressure side is a little bit different. The design is how big is the pressure you want to go. And there you have to be sure that you build in valves that open at 120 or 140 bars, safety valves. On the high pressure side, some made it in stainless steel. Normally, I would say 80% or 90% are working with K65 copper. On the liquid line, we have 2 degrees, normally 37 bar. The first system starting at 2008 or 2009, we start with a design pressure on 40 up to 45 bar. But there you have to be sure if this whole system is standing still, you have to be sure that there is a standstill cooling, right? If you have a failure and 40 up to 45 bar, you see here above 33 bars, it's at 2 degrees. If you remember that this receiver is standing in the machine room, and the machine room is not cold. The machine room is always at 20, 25 up to 30 degrees. Then you have to remember that the the 30 degrees of the machine room is going even into the receiver, right? If the system is standing still. Trend is definitely going to 80 or 90 bar safety for the liquid line. The suction sides, we get it from the manufacturers of the compressors. Even we get this data from BOCK. So, any questions so far? Yanni, did we receive any questions? I see he's shaking his head, but he's not sleeping. He's just shaking his head because I was asking him, but I even did not see any questions, so I explained it previously in the right way. Let's see what is happening on the high pressure side. High pressure side. You have to design your high pressure side as here we see maximum curve at gas cooler outlet at 40 degrees. Okay, but first of all, have a look at COP. What is COP in our cooling system? COP is normally what you put inside a system divided what you can get out of a system, or out of the system in the evaporator, put in the compressor, divided, you get a COP. It's just an example to show what is COP for. Okay? Now, if you put the high pressure higher, then you see, oh, this part is bigger than this part. So the COP is going better. You get a better COP when you are rising your high pressure. When you are rising from 90 bar up to 100 bar. Okay? So, why put the high pressure higher? Because what you get out is lower than what you get in, what you have to put in. So the COP is going worse. So if you see this, and if you do this for several small circuits, then you see that here, if your system is working in transcritical situation, then you'd see here a line. This is a circuit. Remember our circuit in the H-log-P diagram. And here, this is a line that I'm talking about. Transcritical situation. This is a line where our system, our controller wants to get the high pressure side on the best COP. And this line describes the best COP controlling on the high pressure side. So going back to the plus 40 line, this is our design, maximum high pressure side, maximum gas cooler outlet. Okay, and this is the maximum of our system. Empty compressor, gas cooler, high pressure valve, so on. If you're going down or the outside temperature is going down, then our system wants to go down also on the high pressure side, but not here and not there. Our controller is always looking for this point, for this line. Okay? And subcritical, it's clear, subcritical, our gas cooler works as a normal condenser. Then we want to go on the liquid side. Okay? But when we are going back on the highest point. One more, please. Yes, here we are. Highest point? No, I think there will come one more. Yes. I was talking some slides before at the maximum high pressure point, at the maximum gas cooler outlet point. I was talking that the CO2 system divides into 2 points, 57% in liquid and 43% in gas, dividing in the receiver for the gas bypass valve and the liquid line. And this is now the maximum point of our system. Gas cooler outlet 40 degrees. We are on this line, on this point. And now if you see where we end in the receiver, we going into our high pressure valve and coming out in the receiver. And there you see this point or this part divided to the whole line. This is 43% of the whole line. And this is 57% of this whole line. So it's always at the maximum point, working point in our system, you divide into these 2 parts. How big or how small your CO2 system is always this percentage. Okay? So going back, here we are. Booster and parallel compressors. That's our system. Remember, the parallel compressors are only working when the gas bypass valve is closed and the gas bypass valve is only working when the parallel compressors are stopping. That's our thinking of controlling the receiver pressure in a perfect way. Other manufacturers of controllers are doing this in a different way, but our thinking is like that. Okay? So why we are building in parallel compressor? Let's think about remember, we are starting working with CO2 system in 2007 or 2008. There we have a lot of system with R744. So our CO2 system were compared with R744. And it's absolutely clear, and that's effect at the outside temperature of 27 degrees. Below of this, our CO2 systems are working better than 404 system. But above, and sorry, in Germany and in Central Europe, it is normally in summer times, we had a lot of temperatures higher than 27 degrees. Then we are working much we are working not so good as 404 system. But when we build in parallel compressors, then we are putting this point up to 38 degrees. And that's why are we build in Central Europe normally parallel compressors. Just to get a system with a good working COP and a good efficiency. Why we are doing this? You have to remember CO2 system in northern parts where always normally it's cold enough, where we have temperatures normally between 5 and 10 degrees. There we did not have any problems. But if you see Africa or South America or Australia or India and China, then you will see, oh, it's a little bit critical to build in their normal booster system because we are working not good. They are working, but it's better to put to let the CO2 systems always only run in subcritical mode. But with parallel compressors, then we are letting this equator going away, and with ejector systems and built-in ejector, then we can sell CO2 systems all over the world. Transcritical CO2 systems are working all over the world with parallel compressors and ejectors. So, what is an ejector? Sorry, just a small, very small break. Get some liquid for the presentator. So, coming back, what is an ejector? Ejector, as I mentioned before, it's nothing new. And you have to remember when you are a painter for cars, if you put paint or lack on the car, then you always use an ejector. Here you have pressure, here you have the paint, and here you have the car. If you put the pressure in a small nozzle and put there a line in this box, then you have here a suction. It's not going this way, the pressure is going this way. So you suck the paint and put it with the air on the car. And this is what we are doing. Here we are coming from the gas cooler with a high pressure. We put the high pressure in a small nozzle. And when we are going here with a suction from the suction side, then we can suck here CO2 from the suction side from the empty compressors and put this back again into the receiver. Here is the receiver. How it looks like, these are our ejectors in different sizes, and this is the controller for the ejector, our pack controller for the ejector. If you see this is the biggest ejector that we have with 6 steps, but you can put, if you have very, very big systems, then you are able to put ejectors in parallel. So, how it works? Here we are coming from the high pressure side. These are the 6 nozzles. We have nozzles in small, bigger, 3rd step and 4th step, and then we have only 4 steps. So we have 4 steps for nozzles. We are going here for a cleaner. It's just to stop the dirt going into the ejector. And here we are going to the receiver, and this is a suction side. So we are coming here from the high pressure side, put power on the nozzle and open it, and then here we are going sucked over this channel going into the receiver side. I hope now we are We did not test it here, but let's see if it's working. Normally, now here we are. Here you see we are coming from the, oops, sorry, I want to just to break it. Oh, we have some questions, yes. Is there information available about design and selection of components with examples? You remember you're talking about the design pressure of the whole system. Yes. First of all, it depends where you want to sell or where you want to mount the system. If you want to sell the system or mount the system in northern part of Europe, in Sweden or in Denmark, then it's easy. You did not have to think about the design pressure, especially on the high pressure side. But if you want to sell a system where it's very hot, India, China, northern part of Australia, there you have to be sure that your high pressure side is not breaking or it's not exploding. So there you have to think about the high pressure side on the design of the high pressure side. Which working points to consider besides centrifugal mode when to use additional heat exchangers like LTD superheaters, parallel compressors, ejector. If you want to have an heat recovery, then normally, especially like now we are in winter time in Germany, so we are starting the heat recovery mode in all our systems. Then it's clear we are not working in subcritical mode. Why? Because we want to have the maximum of the heat, of the energy out of the system. And the best way to get the energy and the heat out of the system is to work in transcritical mode. So when you are talking about the working points, I'm coming back later, but now I got the question. If you want to have a working point for high pressure side with heat recovery, then I would think normally in our region, so here in Germany, I would configure a high pressure side between 80 and 90 bars. Not as much as your design is able to fulfill. Remember, if you put an relief valve, a safety valve for 120 bars here on the high pressure side, or 80, 90 bars for the receiver pressure, it's not clever. I will show later why. It's not clever to put the configuration on this high level. It's always you have to think your empty compressor. Empty compressor is not the worst thing, but if you put the high pressure point, the controlling of the high pressure point, even when it's cold outside and you're working on heat recovery. So you are working now with a fixed transcritical mode. Then you always have to remember, if you're working higher, then the COP of the empty compressors are going worse. That's the point. So we always have to remember what I can get out at which point of the heat recovery and at which point are our compressors are working how. That's, you always have to compare, right? Okay, I think I explain it as much as I can. When something is not clear, just please come back to me and I will see that I explain it more. But let's wait until the end. I think I will go there on my slides. So this is here, ejector coming from the gas cooler. Here we're going to the receiver, and that's the suction side of our, coming from the suction side of our empty compressors. Let's play it again. Here we are. That's the way how it works. Okay. So now we end it here. I do not know if I stop it or put it only in small. I will stop it. Here you see the several steps. I do not want to start this animation here, but we are starting with the smallest nozzle, then the second nozzle is starting, then the smallest and the second nozzle. It's a binary controlling of the valves here. Okay, so coming back, we have some other things to talk about. There are static ejectors, variable ejectors with only one ejector. And we are not thinking that is clever because you do not have any redundance. If you build an hour ejectors, then you have to see, you always have smileys, because what I see in the outside, in the field, when the manufacturers of the systems are working, are building the pipes and put all things together, there is so much dirt in our systems. When 2007, 2008, 2009, anyone was starting with CO2 and anyone was afraid, oh, it's working or it's not working, these systems are built in a very clean situation. But now CO2, for all of the guys who built the systems, it's a normal thing. So they are not working very clean. So you have a lot of dirt in. And so we see from some ejectors, we get back out of the field, we open it, and we found strange things in our ejectors. So always be sure that the building system is in a very clean way. So here we got our system back again. If we are working in a normal situation, 100% going over the empty compressors, parallel compressors is stopping. We are working subcritical, so we are not sucking here on this side, 100% going here, 70% here, 30%, it's just an example, 30% going over here, and 70 coming from the empty compressor back again. So 30 and 70 are 100 again. But when you are working transcritical, then you will see 100% going from the high pressure side through the ejector. We are dividing here 60%. We are working now transcritical, so 80% are working here, 20% coming back again. And so when you see 20% are here and 60% are here, where are the left 40? 40% are going this way. And it's not, I was not joking, it's 40% that we can select from the empty compressors and going back directly into the receiver without putting any energy on this ejector. So how the system is working. Oh, I don't think. So just stop. Here you see normal system, very warm outside temperature. Empty compressor is working. IT compressors, parallel compressors is working. This gas bypass valve is stopping. So we are coming with the high pressure side over 73 bars. So for example, make 80 bar or 90 bar. We are going here, going into the ejector and dividing it into the liquid line and sucking out of the suction side of the empty compressor. Here you see the several steps working of the ejector. But normally, the ejector is not only working for higher outside temperatures, it's also working in cold condition. So when it's cold, when we are working subcritical, we are not here have so much mass flow. The IT compressors are not working. Empty compressors are working. We are here now working with a pressure 55, 50 or 60 bars, not higher than that. So you do not have to use a separate high pressure valve. So it's wrong. Let's say I am from Danfoss. So if you want to be absolutely sure and absolutely safe, then please build in parallel to the ejector a high pressure valve from Danfoss. Normally, no, it's a joke. I'm not a sales guy. I'm a technical guy. So if you want to build an injector, it's enough to build an injector. You do not have to put in parallel here a high pressure valve to control the high pressure side. Okay. Ich sehe, es ist 5 vor. Alles gut. Oh, was ist jetzt? Ah, here we are again. Functions of the ejector. We are not showing animations anymore. Now we are coming back to the facts. If you put this into a graph, then you see here when we are working without ejector and with ejector, then you see on the suction side of the empty compressors where the pressure is going down, especially when the ejector is starting to work. Energy saving, we are talking about especially in Europe, very deep in energy saving. So if you have a look on the outside temperature, as high as better the saving. So we are talking about gas ejectors, high pressure ejectors. We have a very good controlling of the high pressure side. We optimized with parallel compressors the COP of the whole system. Ejectors built in. We are sucking here. What else? What else can we do? What else can we do? If you see the cooling, the coolers for the cabinets or for the cold rooms, then normally we have to be sure that on the suction side you do not get any liquid, right? So when we work with our AKV, with our electrical valves, then we always control here a positive superheat, right? Because only when we are positive on the suction side, then we did not get any liquid. But when we control the coolers with positive superheat, then we are not working the whole area of the cooler. We are using a part only for the superheat. We are not using this part for cooling the goods, for cooling the temperature in the cold rooms, right? So isn't it clever to use the whole cooler for cooling down the goods, the temperature? Yes, but how? It's now we have a special function in our case controllers. If they get a signal, then they do not control the superheat here at the end of the cooler. Positive superheat. They are controlling the superheat by 0 degrees. So we put more liquid in the cooler that we use the whole cooler for cooling down the goods. But if you do this when you here did not have any superheat on the outlet of the coolers, then you have to be sure that this liquid will not go into the compressors and will disturb them. So you have to build in a divider, liquid divider. But how to get the liquid out of this part? Build in a liquid ejector. Liquid ejector is starting with a suction, with sucking on the suction side very earlier than the high pressure ejector. Okay, and there we get the liquid out of the suction side of the compressors and get it in back into the system. So this function we are calling ALC, adaptive liquid control. Here you see in a big system, coming back to the liquid separator, there we have 3 measurement points, one below, one at 30% filling, and one at 80 or 90%. Going back to the high pressure, highest measurement point, why we have there, if something going wrong with this controlling, with the RLC operation, and the system is filling up with liquid, then you have to be absolutely sure if you rise this point, 80 or 90% filling of the separator, then you have to stop the full system immediately, because our compressors like this are no pumps, definitely no pumps. They have to suck gas and no liquid. So why are the other 2 points there? 1 point above at 5% or 10% below the lowest point. Then if the liquid is going down, then we start the RLC function in our case controllers. They are controlling the superheat at 0 degrees at the outlet. The liquid is coming into the separator at 30 or 40%. We are stopping this. The signal is going back to the system manager, sending over the bus the signal, okay, now you are controlling again a normal superheat, and the ejector is sucking the liquid out of the separator. Here you see this circle in something wrong? No? Everything clear? Okay. You get this presentation. I will show over here the overview. I have to hurry up a little bit because Michael will also tell you something, but let's get back to the heat recovery. Heat recovery, here you see an overview what we are talking about, the heat recovery. Here we have the empty compressors. Here you see the first step of the heat recovery, second step of the heat recovery. First step, we are talking about heating up tap water. Second step is heat reclaim for heating up the building. And only one controller is controlling the whole site. Here you see again the heat recovery for tap water and heat recovery for the more normal heating of the building. And here you see I'm talking about not to go as high as you want with the pressure of the system. Here you see why I'm talking about this, because you always have to recognize that all our system, of the cooling system, we have a COP, of the heating system, we have a COP. So there are several things to recognize, and several COP have several curves. And if you see the best envelope to let our CO2 system work in transcritical mode is not 90 or 95 or 100 or 110 bars. No, it's between 75 and 85 bars. So remember this, and that's not only Danfoss is saying, it's just ask some heating guys and they will explain this also to you. So what else do I want to show? Coming back to some slides for what we are else doing. Our system managers are controlling not only the cooling system, they can also control climate, light, and something else at heating or controlling the whatever you want. From Danfoss, you get anything you want to be happy, but in our times now, I always have to tell you that we have some delivery problems. So if you want to order something, then be happy if you get something. But normally, any parts of a cooling system, Danfoss is able to deliver. Starting a frequency converter, starting a valve, starting a gas warning system. You can get anything out of our delivery parts. So I will end at a little bit time over 10 o'clock. So I think Michael is happy that he is starting so early. Do we have any questions? I do not see anything anyhow, but remember, I will come back at 1 o'clock. We will see then when we're starting the rack here. I will coming back, and if you have so far any questions, just please write it in, remember it, and coming back to me. So have now fun with Michael. See you.
Thank you. Thank you very much, Knut. So, always great with Knut. Just a second, we have to put up the original presentation. Yeah, now you could see yeah, a lot of things about the controllers and how CO2 applications work. You just have to find the right presentation. Yeah, yes. Oben. Yeah, and in the next 40-50 minutes, we will talk about our compressors. Also very interesting, of course. That's why we are here today. Okay, so at that part, yeah, we will start. Yeah, the question why natural refrigerants. I mean, every one of you have discussed this point a lot of times and have heard about it a lot of times. The standards and the regulation are going more and more in natural refrigerants. We are going away from the synthetical refrigerants. Why? Of course, of the natural of the environment, of the global warming and all these themes. But you guys, you know why you are here today, and I think every one of us is yeah, clear that we will have in the future much more applications with natural refrigerants. And I think it will be normal for us in about, let's say, about 5 to at least 10 years that we will work most of the time with natural refrigerants. Yeah. Footprint, CO2 footprint, yes, of course, we want to leave for our children, for our grandchildren. We want to leave a world where they can also live in that world. It's also very important, and we at the company BOCK, we see it as a big responsibility also of our side. BOCK compressors, yeah, well known for most of you guys. I mean, we have a quite wide range, also of course for synthetical refrigerants. I have a small overview of our whole system or compressor range that we have. Medium temperature applications, and for low temperature applications, we have special compressors, as you can see in our catalogs. But today, of course, we are talking about our CO2 transcritical and subcritical compressors. Why that? You could see that at the explanation of Knut. We have separating a CO2 booster system in a subcritical part and in a transcritical part. So, and we here at BOCK, we have a really wide range, meanwhile, of CO2 compressors. So, I'm starting just with the subcritical compressors of our range. Here you can see the smallest, the HG-X12 subcritical. It's the smallest up to the HG-2022. These both are 2-cylinder compressors. Then we have the HG-34. This is a 4-cylinder CO2 subcritical, and the biggest subcritical, the HG-X44. What we have very new now is the HG-X24 CO2 LT. LT stands for low temperature. We have the same model also for high temperature as a transcritical. This is a mixture. Why? We can see, I think Knut also talked about it, we can see more and more application designs with higher pressures, not only on the discharge side, also on the suction side. So if you look here, you have the possibility. I hope you can see my mouse here, yeah. It is designed for the pressure design, low pressure, up to 100 bar, and high pressure also up to 100 bar. That's the new HGX24. He is available since last year. I think in the middle of last year, and you can have here a low temperature cooling capacity from 7.5 up to 23 kilowatt at a normal point of minus 35 degrees and condensation minus 5 degrees and 50 kilohertz. Yes, you can have that low, the HGX12 LT in 3 versions, the ML, the S version, as the SH version. The ML, you will see that later also. This is for the normal application. S is a stronger motor that you can choose, and the SH is also the stronger motor, but for, let's say, higher evaporating temperatures that you need. So that means our subcritical product range program goes from 1.6 kilowatt up to 49.2 kilowatt with the biggest 4-cylinder subcritical compressor. So you can see you have a really quite great range to choose between our compressors here. Then additionally to this range, of course, now another new thing will coming up in the second quarter of this year, 2022. This will be the HG12 CO2 also LT compressor. It's the same, like I said before, we will have also the possibility to go up here on the low temperature side up to 100 bar. And there we will have also a range then from 1.7 up to 3.5 with this small LT CO2 subcritical compressor. Additional, of course, to the subcritical compressors, we have also a nice range of transcritical compressors. And here we also have now brand new started, I think last week we started with the production and it's released. You can buy the newest 2-cylinder, the smallest transcritical 2-cylinder in our house, the HGX12 CO2T. It's a small 2-cylinder compressor. Then we have, like I said before, the HGX24 transcritical. He replaces the old HGX2, which is, of course, since last year not available anymore. Then we have the HGX34 transcritical, which is a 4-cylinder, and our biggest, the 6-cylinder CO2 transcritical HGX46. You can see also, that the market is looking for very small CO2 compressor meanwhile, but also, of course, for very big CO2 compressors as well. I think the next step that we are going to do, excuse me, will be 8-cylinder for industrial applications. More and more industrial applications, industrial heat pumps are customers asked for that. This is something where we are also replacing a lot of ammonia plants in the market. We see more and more, not the real big ammonia applications, but the small and middle-sized applications. We can see that it changes a bit more to CO2 in the last time. Just a few words about the HGX24 CO2 transcritical. This one, of course, is released to 100 bar on the low pressure side and 150 bar on the high pressure side. Goes from 4.6 cubic meter per hour up to 9.4 cubic meters per hour, and also available in 3 versions: the ML, the S, and the SH version. Maybe we have time later, and we can pop off our VIP, the compressor selection program, where we can see how you can select these compressors. Cooling capacity from 9 kilowatt up to 21 kilowatt with this 4-cylinder transcritical compressor. What's cool about that also is that we have here a 4-cylinder where not all of our competitors have a 4-cylinder, then they have a 2-cylinder. And as you know, guys, outside, a 4-cylinder has always a much more smooth running, much better smooth running than a 2-cylinder. And we are known for compressors, for very smooth running compressors. And this guy here, the HX24, is really, it's for CO2 compressor transcritical, fantastic how smooth he's running. And we have him built in here since almost, I think, almost a year now. He works here in our application as a parallel compressor. Yeah, but we will see that in the afternoon when we start the application. We will try to make a small sound check for you. We prepared microphones here, and so that you can at least hear how smooth these guys are running here. Brand new, the transcritical HX12, even smaller transcritical one, also released for pressure of 100 bar and 150 bar. 150 bar, of course, on the high pressure side. You can use that for medium temperature systems. You can use it as also as a parallel compressor for heat pump system and for air conditioning chillers. It's also available in 3 sizes: the ML, which is totally normal mode size, and the S with the stronger motor, and also SH for heating pump application with higher evaporating temperatures. So that's the brand newest product of our brand in the market. I think we released, like I said, released it last week. Here you can have, you can achieve with 50 hertz, you can achieve a cooling capacity of 3 kilowatt up to 6.5 kilowatt, and of course, even with using frequency converters, you can go higher as well. Compressor design, transcritical. You heard it this morning also from Knut with this high pressure that we have on the discharge side and even on the suction side. I mean, for you guys, 35 bar was quite known. For example, 35-40 bar with refrigerants like in the air conditioning systems with R744, for example. But of course, on the high pressure side, and we have that pressure now here on the low pressure side, and then the transcriticals even up to 150. So that means for us, as you can see on this slide, by the way, you will have the whole presentation. We will send it out to you. I don't know if it's happening today, but at least I think tomorrow to all participants, we will send out our presentations. So you will have that also for you in the office, and you can read them again and or more deeply if you like, of course. And you will have the information at least tomorrow. So just why have we done this with this LP compressors, with this 100 bar suction side, 100 bar discharge side? We can see that more and more, thank you, Yanni, more and more applications are changing the systems. The people build other systems. At the beginning, they as you can see in the picture, they had the normal systems, 100 bar, 30 bar on the high pressure side, and up to 40 or even 30 bar on the low pressure side. That's similar as, yeah, as our system at the moment. We don't need higher pressures here in the training center, so we choose the normal version. But more and more companies outside, yeah, you can see it here with the pressure. More and more companies outside change and design systems with even higher pressures, as you can see here on the low pressure side, up to 100 bar. Of course, that's the choice of the rack designer. He knows, he has to know what he wants and what he needs, and then he has to design his system. But anyway, we are prepared for everything you need in the market here at the BOCK. Operating limits, yeah, you can see it also in the VIP. We have here a small overview. This is the low temperature subcritical operating limits. You can choose here also between a ML, a small motor compressor, and a S version with a stronger motor with higher evaporating temperatures, as you can see here in this chart. This will be the ML up to minus 15 maximum, and then here the strong motor even up to 0 degrees evaporating temperature. In the transcritical size, also the same. Just let me have some water, please. So, yeah, transcritical design also the same. You can see the blue range here: ML small motors, normal motor, S with stronger motor, and SH for heat pump applications. Even you go up to evaporating temperatures from here, as you can see here, over 60, 60 bars, 65 bar, which is quite 20, I think 25 degrees evaporating temperatures. Pressure design up to 150 bar. Yeah. To give you a small comparison, guys, here in this picture you can see the difference between the sizes of the pistons. I think I have them live here also. Just a second. Yeah. Here I am again. Compared, if you take a compressor system with R744, you will find inside the four-cylinder in the HGX44 4 of these pistons, this size, yeah. Okay, and if you compare it now with the same size for the same capacity with the CO2 compressor, then the size of the piston is like this: 4 of them, and 4 of them in 134, and this is CO2. That's due to the big volumetric capacity of CO2. That's really fantastic. So that means, yeah, it's the compressors, the components of the compressor can be smaller, but also, I will just put it away again. But that's also, yes, counts also for the other components like heat exchanger, evaporators, and even the pipings. The size of the pipings, you can choose them much smaller than, as you know it from R134. And that's a part that's very important in my eyes, because of course the CO2 application at the moment is a bit more expensive than a normal synthetical application. But on the other hand, you can save money with smaller piping, smaller evaporators, and so on and so on. Yeah, we will just come to the point safety because of this high pressures that we have here. But believe me one thing, at the first, for all of you who are not working with CO2 at the moment and who will begin to work with it, it sounds a lot. High pressures of 100 bar, 110 in your system, low pressure sides, 60, 55, 60 bar. But after working with it for a while, it gets absolutely normal. That's how my impression was with CO2. Yes. For us in the company, we are building these compressors. That means if you produce a compressor for such high pressures, you have to test them. That means in our production, we make burst pressures, I think, once or twice a year. And that means we have the 3 times of the normal pressure is the test pressure that we do. That's on the low pressure side, 300 bar. And on the high pressure side, up to 450 bar that we put in this compressor. And it's no problem for that. It's not released for application for you. It's just to show you what we are doing here, how we test them, and to get a good feeling that you have a great product, a safe product from our house here. We have pressure relief valves on the low pressure side. We have pressure relief valves also on the high pressure side. For some of you guys who know other compressor, our competitors, you know that they don't have that, or not every one of them has it on both sides. And we do, of course, pressure and leak tests with each compressor in our production. Here you can see the pressure relief valves. Every relief valve in our house has this cap on it. Again, here's a small one. I don't know if you can see it. Here's a bigger one, but you see it also on the picture, of course. Why do we have this caps on it? That's very simple. If you, let's say, you work on the application, you work on the compressor, and something happens and you get a high pressure in the compressor. Can happen. So that means the high pressure of, let's say, 45, 50 bar, the pressure relief will open at a subcritical, at a transcritical, of course, only at 100 bar. And all this pressure won't come directly to you, you know, if you stand in front of the compressor. Because believe me, if you get a 70, 80 bars standing near such a valve and it gets in front of you, it's like a small punch. And we avoid that with the cap, because the cap makes a more surface for the more place for the outcoming CO2, and it goes away from you, not directly to you. Not every compressor builder has this. And of course, our safety valve guys, they're only for our compressors. They don't replace any safety valves in your system. Be aware of that. You have to put, of course, additional safety valves in your system. Here you can see a better picture how the gas flows out of the safety valve in case of opening. Efficiency. Especially our new compressors and the whole range of the transcritical compressors have a really great efficiency. And how do we do that? We have a really clever compressor thermal management. You can see it on the picture here. That's a cylinder head. Here's the small one. Here's the 4-cylinder here. The cylinder head, we separate the two sides, the discharge side and the suction side. That's important because you don't get additional superheat. And if you don't get additional unnecessarily superheat, that means it's good for the efficiency of the compressor. Consequent separation of hot discharge. We have a very low internal pressure and return flow losses. That's also through our design inside the cylinder heads, inside the compressor. Low compressor oil carryover, of course. Why do we have that? In every compressor we have an oil pump. That's standard at BOCK. Every compressor, every size has an oil pump. So individual optimized components, motor, driving gear, valve plates, and so on and so on. The efficiency, the market efficiency is very great at BOCK. And also, as you can see, validation stress tests, what we do with every compressor in our validation office. They have a really hard time there, as you can see in the picture, but yeah, we need it. It's for the reliability. We have to know where we can make the compressor better. How are the parts look after such a test? We are testing everything here for you. So it is important that you have a reliable compressor, a reliable BOCK compressor. Efficiency benchmark compared to our competitors. Guys, this is all with normal standard motors, not with permanent magnet motors. We don't have them at the moment, but we are working on it. But as you know, also, of course, if you have a compressor with a permanent magnet motors, you have to pay, I think, approximately 30% more for such a compressor. So if you compare our compressors with the competitors, with the standard motors, we have a really very good efficiency from 4.4% up to 7.3% higher than our competitors. And what do you want and what does your customer want? He wants to save money. He wants to save energy costs. So the BOCK is the right choice for you and your customer then. Durability. We have a high pressure design. We have the highest efficiency that is certified by the ASSOCOM. We'll show you that later. We have oil pumps. High reliability with optimized drive gear. Operating limits for each application. 3, we talked about that. Excuse me. Variable speed drive for all compressors, of course, 20 to 70 hertz released for the 4 to 6 cylinders. And we have a very low oil carryover due to our oil system. That's very important. With 50 hertz, only 0.2% of the mass flow is the oil is the part of the mass flow. With 60 hertz, only 0.5%. Optimized valve plates as well, very important. We check the simulation. Yeah, we with several programs. Meanwhile, that we have in the house, we check the optimum of the gas flow in a valve plate or in the whole cylinder head. And through our construction, we have a low backflow of the discharge gas. And high reliability of because of our anti-dirt pockets under the discharge lamellas. I will show you. This is also something special that we have. I hope you guys can see that. I just checked that here. Yes, you see under the lamella these pockets that are in the material phrased in. Maybe it's better like more inside. Here under these lamellas. Yeah, guys, you can see these pockets. Yeah. Where are these pockets here? They avoid, let's say you have a bit of dirt in the system. Or yeah, it's a bit of dirt in the oil or whatever. It won't block your lamella. If this dirt comes to this part, then through this pocket, the discharge gas, if there's dirt under the lamella, the discharge gas can take it with it. He has a very high speed discharge gas, we know that. And so you avoid to collect dirt under the lamella. So what happens if you don't have this, or what could happen? What could happen is that your lamella, without dirt pockets, the dirt is under the lamella, you get more and more dirt, and the lamella, let's say, goes that way. Yeah, it's not straight like it should be, it goes like that, because the dirt under the lamella, and then it can break. And nobody wants a broken discharge lamella in the compressor, because what happens, you get the backflow, the discharge temperature gets higher and higher, and poof, that's it. It's not good for your oil. Your oil gets burned. Then in this cylinder, the piston will have a damage as well, and the surface of the piston. And that's why we have in every of the CO2 valve plates this anti-dirt pockets called. Yeah, really a good thing, great thing. So we'll bring that back. Yeah, we want to show you also something inside our compressor, because that's important for the reliability. Not only outside they look fantastic, but inside also. The compressor oil management. Just a few words about that. That's our philosophy. The oil pump in every compressor. I think you can see it here. Due to the oil pump, the oil level, we can keep it very low in the compressor. So that means you will always see it in the side glass. And if you compare it to others who don't have an oil pump, they will have a much more turbulences in the side glass than our compressors. The oil pump sucks the oil and brings it directly there in the crankshaft, directly there where we need the oil, guys. Yeah. So we have a fantastic oil circulation inside the compressor. We have a great oil refrigerant separation. We have also a separation between the motor side and the crankshaft side. And if you compare it here, the open oil management, we can reduce with our special optimized oil management, we can reduce the oil flow, the oil throw in the system. And I think everybody of you knows, first, it's good to have the oil there where you need it, and not in other components where you don't want it, or you don't want it more than needed. Evaporators, for example. So that means with optimized oil management, you have also a better efficiency in your system. That's also very important. Operating, yeah. Like I said before, you will hear in the afternoon a very low pulsation that we have here with our compressors. We have operating conditions, LT, empty, and for high pressure applications, for heating pumps, we have a variable speed drive. For the 4 cylinders, up to 6 cylinders, we can go 20 to 70 Hertz. For the subcritical 2 cylinders, 30 to 70 Hertz, and for the 4 cylinders, 25 to 70 Hertz. We will show you that also in the afternoon, because every compressor on our application here, on our rack, has a Danfoss variable speed drive. You can see them on that side. You will see it later. We will show you the frequencies. Flexible connection are possible. You can turn that in any way you want. The valves, compact dimensions, very low noise level, and a very good running behavior. Talked about it. We do that through a good mass balance in our compressor design. And low pulsation also, of course, a low pulsation. Yeah, how to achieve that? Of course, if you work on your cylinder head, you have a high discharge volume, of course. We have pulsation dampers inside the cylinder head, what lowers, of course, the pulsations, which are also, this point is also very necessary. You don't want to have high pulsation, discharge pipes, of course. And all our programs, I will show you that later, the programs that we have. Oops. What happened now? So the whole product range for transcritical is up from the HE12, from the smallest 2-cylinder, from 1.7 kilowatt up to 38.2 kilowatt with our biggest 6-cylinder HEX46. So we have 4 model sizes with 19 capacity stages. I think that's a great range. Cooling capacity from 3. It's not true. We forgot now. They were from 1.7 to 85, and heating capacity from 9 up to 182 kilowatt in all the system. What we also want to show you, because I don't know, most of you maybe know it, we have a bit of separation in the company. We have a stationary part, which are we here, with guys with the stationary compressors. But we have, of course, also a mobile part. Our colleagues who work for the mobile part in the company, the mobile compressors, FK compressors. And I just want to show you a small overview of what is happening here. I mean, the future is, or the future drives electric. You can see that it started with the buses here in Germany or worldwide. Meanwhile, we have more and more electric buses. But also when I look in the paper, I see that the numbers in the newspaper, of course, as you can read, that the numbers of electrical vehicles in Germany, in Europe, is rising. Really, really very strong. But we are working especially on the bus systems and train systems and ship systems, of course, not at normal cars. And in the bus systems, you can see here the first trials have been in the 1970s, even with here you can see additional, how you call it, on the back with all the batteries inside. First Electrobus 1970, and meanwhile we are here, actual highlight, technical highlight, AC Taro from Mercedes-Benz. And inside such electrical bus, You don't have so much space. You need small components, small compressors. So our innovation here since last year, or even 2 years, meanwhile, is the BOCK HGR40. It was the first one. And since last year, available also the HGR60. The 40 is a 4-cylinder, the 60 is a 6-cylinder. It's a so-called star compressor. It's a transcritical CO2 compressor, a full hermetic, as you can see. This was a cooperation development with Mercedes-Benz, together with Mercedes-Benz and Convecta, who are building air conditioning parts for Mercedes-Benz or other bus brands as well. Project started even in 2013, and the result was the world's first serial CO2 heat pump system for electrical buses, powered by the BOCK HGR40. We are very proud of this. It's meanwhile very successful. Yeah, because to have a CO2 compressor in such a small size in an electrical bus gives you a lot of possibilities. You have electrical bus, you have to cool, of course, also in the summer, but you have to heat in the winter. You don't have a normal motor as you know it before, because the motor gave his warm power to the inside of the bus, and so you could heat the bus, the heating power. And that's not possible with the electric bus, and that's why you need a really efficient compressor to get as much heat as available as possible in the bus. So this is the solution from BOCK, a fantastic compressor, 4 and 6 cylinders available meanwhile, welded steel housing, high efficiency, and a really, really great frequency range. You can drive that guy from 12.5 hertz up to 75 hertz. At 4-cylinder, the HE60 is a bit lower. You can drive it maximum to 65 hertz, but also down to 12.5 hertz. That means you can have an optimal coverage of heat pump performance requirements and for the whole thermal management in the bus. I think yes, in this buses even they also have to cool the batteries in the summer as well. So really a great compressor, and that's really robust design with high performance, also with oil pump. Is it right? I think you can see it here how the system works. Does it work, Janni? Die Kolben drehen die sich? Yeah, you can see the star compressor system in this film here below. That's how this compressor works. Displacement from let's say the small one 7.3 cubic meter per hour and the big one 10.9 cubic meter per hour, with 50 hertz, of course. Capacity for the small one, for the 4-cylinder HR40, from 7 to 35 kilowatt. Cooling capacity, heating capacity 4 to 27 kilowatt. And we also have, of course, here for 100 and 150 bar pressure in the system. Yeah, that was our also a very new invention, the HR compressor. At the moment, more and more companies ask, oh, can we use it also in stationary applications? Yeah, we're working on that. And normally you can use it, of course. It's at the moment in the market for buses, but I think we will see this guy also in smaller heat pumps and in smaller cooling solutions. With CO2. For you guys, what we also have, of course, we have our VIP, our BOCK selection program, which you can find in the internet. Really good program. Können wir das kurz aufmachen, oder? I will just show you in a few steps. I think we have a few minutes left, yeah. Yali will open that for us. Just give us a few seconds, please. So the program is in the internet, but you can load it down, of course, as well. And then you have it on your personal computer, but I would suggest to work always on it on the actual internet version, because here you have always the newest data inside, you know. So, okay, here on the BOCK page, you can find also the VAP. It does not work at the moment. Mach's doch von Hand rein, Janni. We don't have an internet connection at the moment, it looks like. That's strange. Okay, maybe we can do that in the afternoon as well. At the moment, we have small problems here. Okay, guys, yeah, really a great program, but here you can only select one compressor, data for one compressor. If you want to collect, if you need information and you want to calculate a system, a rack system like this, then you can use our BOCK CO2 tool software. It's an Excel-based software. We will please get in contact with your sales manager, with the responsible one, and he will send you this program. With this special CO2 booster selection program, you can design a booster system, low temperature, middle temperature, and parallel compressor. Or you can design only a booster system with only low temperature or only middle temperature. You can design also a heat recovery. The software tool is based on Microsoft Excel. And yeah, that's a product that we have. And we can send it to you. You can start to work with it. And you can also make a small, here, software is available on request. Just get in contact with us. We will give you the software. Here you can see the software on one side. On the left side, you can choose what you need, the capacity of your system. Or it's only for CO2, of course, the rack system for CO2. The capacity of the system on the low temperature side, on the middle temperature side, and the parallel compressor as well. Then in the middle part, you choose the compressors, and then you will have always the results on the right side. So input, you get output, low temperature, middle temperature, parallel compressor, as you see down on the downside. You get all of the data, calculated data. You will see them also as well in this program with temperatures and pressures. Okay. Middle temperature, subcritical compressors, transcritical compressors, everything that you want, you can find inside here. It's really also, like I said before, if you start with CO2 to get a bit of training, it's also good. You can play around here with the working points and so on, with the compressor sizes, and get a better feeling for CO2 applications. Okay, we are coming to the end of the first part. What we also thought is important to show you is safety components in the CO2 system, especially here in the machine room. Yeah, we know if you breathe in too much CO2, it's not good for your health. It can even, yeah, you can get a really worse problem. So every system has to have safety components in the machine room, as here. Or even if you're in you don't need it in the supermarkets inside, but if you have cabinets or storages, you need that inside them. In our system here, you can see we have CO2 detectors, for example, like here. We have 2 of them in our room here. We have a ventilation, that's on that side. It's on the side we will show you in the afternoon. If you have time enough, we will have a small test in the afternoon. We'll do a test run. Important is that your power sources here is not the same power source as you have on your power source for the rack system, of course, yeah? This has to be a separate one because in case of you have power source problems in the rack system, this one should work in case of a leakage in the machine room. You need an optical signal, a flashing indicator. You will see that later here, or you can see it here, for example, so that you can see, okay, there's something wrong here. We have alarm. Or you have, of course, additional also acoustic signal that you need, so that you can hear also, oh, something wrong in this room. Maybe it's better if I get outside. The stage, we have 2 stages here in our system. We have the first stage is a pre-alarm at 5,000 parts per million. Then the optical display starts and the mechanical ventilation is activated. The system will still run then, okay? But in the second stage, if the amount of the CO2 in the gas gets higher, then you get the main alarm, 10,000 parts per million. Then you get additional the acoustic alarm signal and the shutdown of the whole system. Yeah. Here we have an inspection of the system at least once per year, and I think that's also in a supermarket. I'm not sure if it's once or let's say maybe it's twice also, but I think once is enough per year to test the system. And like I said, if you have time in the afternoon, we will make a small test. We will show you what is happening here because I think this is also very important. Or it is very important if you work with CO2. Okay, guys, I think that's from my side. I show you all of the compressor of our product range that we have that is available. If you have questions additional to that, I mean, we can talk, you can ask now, but all of our technical guys here in the house or your sales managers or just, yeah, the contact persons that you have here in BOCK will give you all the information you need. Like I said before, you will get the presentation as a PDF as well. On our website, you can also find much more information about our products. And I think, yeah, so that was the first part. We are really good in time. It's 11 o'clock. Yanni, the VIP still not work? We have to look what I will show you, of course, the VIP in the afternoon then. Okay. That's for my part. Nee, das machen wir. We'll do that later. Okay, guys. So, I wish you here, it's 11 o'clock now in Germany. I wish you a good lunchtime. We will have a break. We also have to eat something, to drink something. And we will be back at 1 p.m. here, right here, same place where we start the system. Thank you up to now very much. Thank you very much for participating, and see you in the second part at 1 p.m. See you later, guys. Bye-bye.